Welcome back to Calc 2 Integral Calculus. So we are now on Module 2. Module 2 will deal with your techniques of integration. If you recall, for this particular course, we are co-presenting or co-lecturing the subject, me, Engineer Guzman, and Engineer Angloan. So for this Module 2, I will be your lecturer. We're going to start Module 2 with Unit 1 integration by parts. Okay. So Module 2 deals with the different techniques of integration. These techniques are applied, coupled with the basic formulas for integration to solve a bit more complicated integration problems. Okay, so we'll deal with integration by parts first. Now in this particular unit, we just simply need to evaluate the antiderivative or the integral of the product of a function u and the derivative of dv. Okay. So what is integration by parts? So if you recall your product rule in differential calculus, that is derivative or the differential of uv, u and v being two separate functions, okay, you'll get u dv plus v du. This is the product rule. Now since we are in integration, if we try to transpose, okay, this v du term to the left side and then isolating u dv, we get this expression, okay. So if we integrate both sides, what are we going to get? So integrating u dv, this is now u dv, okay, is equal to the integral of the differential of uv, of course, is uv, and then minus the integral of v du. This is the basic formula or pattern that we're going to follow to solve problems in integration by parts, okay. You'll notice that integration by parts and algebraic substitution and among other methods of or techniques of integrations, okay, are simply ways in which you can simplify your integral. At the end of the day, or at the end of the solution, your integral will now be solved with still basic integration formula. So a good background on Module 1 is needed in this Module 2. Okay? So we're going to follow this particular formula. Taking note that this formula or all of the components of this formula must be present in order for us to use it. If none of them or if some of them are missing, we cannot use the formula readily. Okay? Now, what are the possible cases for integration by parts? Integration by parts is a very good technique because it deals with now the mixture of the different types of functions, whether algebraic or transcendental function. When you say algebraic functions, these are your functions with your common variables, let's say x plus y plus z. Okay, algebraic processes. When you say transcendental functions, these are your functions that contains exponential, logarithmic, trigonometric, inverse trigonometric functions. In our previous examples, although we do have some examples wherein some functions are mixed with other functions, those examples can be solved easily by the use of the basic integration formulas. But as you go into higher or more difficult problems, you'll notice that functions can no longer, or the integrals can no longer be solved now by the basic integration formulas. Therefore, we need to apply the principle of integration by parts when we now have two or more functions, okay, on the same integral. So for example, we have this one, that is x, that's an algebraic function, and then e raised to x, that is a exponential, that is an exponential function. Okay, so that is already a problem or integral that can be solved now using integration by parts. There will be no available, okay, or this integral cannot be solved merely by the basic integration formulas. Okay, so this is an algebraic function that is now coupled with an exponential function. Okay, this one is an algebraic function coupled with a trigonometric function. This one is an exponential function coupled with a trigonometric function, and this one is an algebraic function and a logarithmic function. Okay, notice here that we are indicating u and dv. What is u and dv? That is the first part of your integration by parts formula. So in this particular technique, we are going to identify a u and we're going to identify a dv. Okay, so that's very clear. We're going to identify a u, we're going to identify a dv. And then we're going to identify a du from the existing u, and we're going to identify a v from the existing dv. How do you get du from u? You differentiate. How do you get v from dv? You integrate. So here we're going to integrate and we're going to differentiate at the same time. But your choice of u and dv is very important because wrong choice of terms, meaning wrong solution, or the integrand will not be solved or will become more complicated. Okay? So let's now proceed to example number 1. So for number 1, we have a very easy one. That is just the integral of x e raised to x dx. So since integration by parts is a good technique to use when your integral is a combination of different types of functions, this one we have an algebraic function, and then here we have an exponential function. Okay, so let's try to solve this using integration by parts. So for the formula in integration by parts, we must first need to define our u and our dv. U will then be differentiated to solve for du or to get du, and then dv will be integrated now to get v. Okay, so the choosing of u and dv is very important. This process, okay, will determine if your answer is correct. If you choose the wrong u and dv, your problem or the integral will either be wrong or will result into a even more complicated problem. Okay, so let's say arbitrarily we have our two terms here, x and e raised to x. We choose, okay, our u as e raised to x, and then we choose our dv as x dx. Okay, so of course, if you have now u, you must solve for du, that is the differential. So the differential of e raised to x is e raised to x dx. If you now have v, dv as x dx, okay, that will get you the integral of integrating dv. It will now become v, therefore 1/2 x squared, our formula. Okay, so you now have u, you have du, you have dv, you have v. So you simply now input them into your integration by parts formula. So what will happen? Let's see. So u times v, that is 1/2 x squared e raised to x, okay, minus this will now become v du. So that is integral of 1/2 x squared e raised to x dx. So if you look at here, on the right side of the equation, or on the rightmost side of the answer, okay, this is still an integral sign, correct? Therefore, we must now also integrate this, okay, side right here before we can produce an answer for the integral. However, the integration resulted into a more complicated integral. Therefore, this gives you an idea that this is the wrong solution, meaning you chose the wrong u and you chose the wrong dv. Okay, so that is wrong, meaning if your integration process resulted into a more complicated integral, that might be a sign that you chose the wrong u and dv. However, let's say another solution, if this time we let u be equal to x, and then dv be equal to e raised to x dx, okay, solving for du, so differentiating u, we get dx, okay, and then solving for v, integrating dv, we get the integral of e raised to x dx is simply e raised to x. So we now have u, du, and then dv and v. Simply inputting them into the formula, what will happen? U dv, that is x times e raised to x, this one, minus the integral of, we're following the formula, v, e raised to x dx, that is e raised to x dx. Notice here that this is no longer a combination of two types of functions. This is merely an exponential function. Okay? Unlike here, what happened to this? It's still a combination of two functions. Okay? This one is a bit simpler. Right? By removing the function x, or by eliminating the algebraic function, this second term becomes now an easy integral. That's just the integral of e raised to x dx. So this is not yet your final answer. After you've written the formula for integration by parts, you must again now integrate one last time. If you integrate this, it becomes e raised to x, correct? There is no longer any integral sign in the solution, therefore plus c can now be added. If you factor out e raised to x, this becomes now your integral. Okay? So this is the correct solution. The correct solution will always lead you, okay, to the elimination of the other type of function. So that's an idea on how you solve integration by parts. Always, okay, at some point, one type of function will be eliminated. If the other type of function, okay, or the functions are not being eliminated, and opposite are now being increased in degree, okay, therefore that gives you an idea that the solution might be wrong. Okay, so the choosing of u and dv is very important for the integration by parts. Okay, so I hope that was clear, and I think now we can proceed to a more difficult problem. How about this one? This one is a combination of an algebraic function and a trigonometric function, the integral of x squared sine x dx. As always, okay, your goal is to remove, or the goal, okay, is to simplify the integral using the formula by integration by parts. Okay, the solution requires you to choose your u and requires you to choose your dv. Okay, so what is your u, what is your dv? If we recall example number 1, when we chose the exponential function as u, when we differentiated it, the exponential function was still there, e raised to x. Here, if you choose the trigonometric function sine x as your u, if you differentiate sine x, it becomes cosine x. Therefore, the trigonometric function will not disappear. However, if you choose x squared as your u, it becomes now 2x dx, correct? If you differentiate x squared. What happens to the exponent of x squared? It went down 1 degree, meaning it's just close to disappearing, okay? Meaning it will now eventually disappear. So I think the right or the correct choice for u is now x squared. Let us now let u be equal to x squared, and let us now let dv be equal to sine x, okay? So it's just a arbitrary choice. It's up to you to make the choice for yourself, but you see, if the solution gets complicated as you go along, then you might want to consider choosing another path or solution. Okay, so again, letting u be equal to x squared, letting dv be equal to sine x dx. Okay, we get du, differentiating u, we get 2x dx, and then we get v, integrating dv. What's the integral of sine x dx? Negative cosine x. Okay, so we now have the terms for the formula of integration by parts. Simply input them into the formula. What are we going to get? So u, v, x squared, negative cosine x, minus integral of v, negative cosine x, du, that is 2x dx. So if you notice, this first term is already okay because there is no longer any integral sign here. Okay, so we can simply rewrite this as negative x squared cosine x. But this second term, okay, this second term, so simplifying negative times negative, positive, factoring out 2, okay, this one, x cosine x dx is still a combination of, okay, is still a combination of an algebraic function and a trigonometric function. But sir, you told us a while ago that integration by parts, if the solution yielded by your initial, okay, choosing of u and dv gave you a more complicated integral, then that means your answer is probably wrong. Well, that's true, but this is not a complicated integral, correct? In the previous example, example number 1, the degree of the algebraic function went up. Therefore, it's not close to disappearing. But here, from x squared, it went to x. That simply means that it's close now to becoming 0, or the exponent of x is now close to becoming 0. Okay, so this is not a complicated solution, although it is adding another step. Probably the nature of the problem requires multiple techniques of integration, and that's okay. And this example can easily be solved by another integration by parts. This time we're only considering x cosine x dx as the integral. So this is already okay. The first term is already okay. We're just going to solve this one on its own or independent. Okay, so here we again use integration by parts, choosing again another u, choosing again another dv. And I think if we choose u as x and we choose dv as cosine x dx, we can now solve the problem. What will happen? If x is your u, du will become dx. If dv is cosine x dx, v becomes sine x. Okay? And if you notice, applying the formula again, so just copying the first term, plus 2. Don't forget 2, okay? So 2, that is the, then integration by parts here. U times v, x times sine x, that is that. We're following the integration by parts formula, minus the integral of the second term. Integral of v du, that is just sine x dx. Notice here that there is no longer any algebraic function. So that's what I meant by it will eventually disappear, or the other function should eventually disappear. From x squared, it went to x raised to 1, it went to x raised to 0. And this can now be integrated using the trigonometric formulas. What's the integral of sine x dx? That is negative cosine x. This is already okay. There's no longer any integral sign here. Okay, so don't forget the 2, and then x sine x minus cosine x. This becomes positive. Multiply 2, distribute it to the terms. That is negative x squared cosine x plus 2x sine x plus 2 cosine x, of course, our constant of integration. Okay, so here we have discovered that the integration, or the techniques of integration, namely integration by parts or by parts, can be used multiple times on the same problem. Okay, so if you analyze further, if this was x cubed, correct, then we're going to have 3 integration by parts until the algebraic function disappears. Okay, so that is your solution. Again, the basic formulas are still present here, or are still going to be used in these types of problem. Example number 3, the integral of ln squared x dx. Okay, so this is another one that can be solved now using integration by parts. Take note, this ln squared x can be written as quantity ln x close quantity squared. Okay, it is not ln of x squared. Okay, so let's make that clear. That is quantity ln x close quantity squared. Okay, so you might be wondering, there is only one type of function here, that is your logarithmic function, because you see ln, right? But sir, does this require integration by parts? Well, if you say no, you might want to try the basic integration formulas, and I think if you do that, you will not be able to solve the integral. Okay, so let's try to do it using integration by parts. And in fact, integration by parts, it's already giving us which one is u and which one is dv. Remember, u will be differentiated, dv will be integrated. If there is only one term here, that is ln squared x, and then dx, of course, automatically, the one that's going to be integrated, dv, will be dx. And the one that's going to be differentiated, that is u, will be ln squared of x. Okay, so the choice is pretty much laid out for you. So we simply get u equal to ln squared x, so that is simply ln of x quantity squared, and then dv is simply dx. Okay, so integrating dv or dx, of course, you get x. Differentiating ln squared x, this is now the power formula for your differential calculus. That is 2 ln of x and then raised to n minus 1, 2 minus 1 is 1, okay, and then multiplied by the differential of u is 1 ln of x, that is dx over x. So we now have all of the factors or components of your integration by parts formula. So we simply write the formula, that is u times v, x ln squared x minus, okay, that is v, that is x, right, and then du, 2 ln x dx over x. Notice that x can be cancelled out, 2 can be factored out, leaving you with ln of x dx. This is again a problem by integration by parts. Or can it be solved using the basic integration formulas? Let's see. Can it be solved using the power formula? No, because the exponent is 1, ln of x raised to 1, but the differential of ln of x is dx over x. There is no x here, so it cannot be solved using the power formula. So we need to again perform, okay, another integration by parts. Notice also what happened to the exponent of ln. It went down again, okay. So slowly, or one by one, the exponent should diminish, okay, so that it can now be solvable by the basic integration formulas, okay. So again, similar to this first integration by parts, we let u, ln of x, be equal to ln of x. We let dv, of course, be equal to dx. And differentiating, we get u, the differential of ln of x is simply dx over x, and the integral of dv, of course, or dx is, of course, x. Okay, so take note how we are integrating this independent of the first term. So just put the first term here, don't forget negative 2, okay, and then a bracket, so that we have our individual or independent integral here. That is uv, so u and v, x ln x, minus, again, v du, integral of v du. X times dx over x cancels out. Okay, this becomes now dx. This becomes positive because we're going to factor in your 2. So distributing negative 2, this becomes negative x ln of x plus 2 integral of dx. What's the integral of dx? Of course, that is x. Since there are no longer any integration sign or integral symbol, we can now add the constant of integration plus c. Okay? So that is how you integrate example number 3. Okay. Example number 4. This one is a interesting one because this is an example with a recurring integrand. What do you mean by recurring integrand? Okay. So you might be wondering, sir, this is another single function. That's just a trigonometric function, right? Secant cube x dx. Okay. So there is, or we do have, okay, a topic for module 1, that is the transformation of trigonometric functions, that deals with the powers of tangents and secant. So you might want to consider that here. But now we're going to solve it using integration by parts. Okay. So look at here. What did we do here? U being equal to secant x, and then dv being equal to secant x squared dx. So unlike the previous examples, I did not let dv be equal to dx alone. What we did is we separated secant x and secant squared x from secant cube x. Okay? So what happened? If we let u be equal to secant x, this becomes secant x tangent x dx. That's the differential of secant x. And if we integrate dv, the integral of secant squared x dx is tangent x. Okay? So if we follow the formula, that is u times v, so that is secant tangent, okay, minus integral of v, okay, du. That is tangent x multiplied by secant x tangent x dx. So secant x, 2 tangent x, so tangent squared x dx. Okay, so if you remember the identity, or we're now going to integrate this, correct? So if you remember the identity for tangent squared x, that is secant squared x minus 1. So substituting, correct, we get now another term here. That is what? Negative integral of secant cube x dx. So this is what I mean, or this is what we mean by the recurring integrand. This was the original integral, correct? This is the original integral that we have, the problem. So here, right? So integral of secant cube x dx plus, so secant x times 1, that's secant x dx. So on the left side of the equation, we have integral of secant cube x dx, and then on the right side we have a negative integral of secant cube x dx. So notice, if you transpose to the left side, okay, if you transpose negative secant x dx to the left side, it becomes positive secant cube x dx. That is now to be added to another positive secant cube x dx. So this becomes 2 integral of secant cube x dx is equal to, what's that? Secant x tangent x plus, okay, the integral of secant x dx. Okay, so what happened here? We are now having two, okay, we now have two integrals. Don't worry, because this is our problem, correct? This is what we're trying to solve for. To solve for the integral of secant cube x dx, you simply need to remove 2. Okay, this right side can be integrated. Yes, the only integral left on the right side is the integral of secant x dx, which has its own integral, that is the ln of secant x plus tangent x. Okay, is there any more integral on the right side? None, correct? So we can now add plus c. So what about this one, the integral of secant cube x dx? Well, that is our problem, correct? As the recurring integrand, correct, was simplified. So we now have to solve for the integral of secant cube x dx. We simply divide the right side by 2, and now we have the answer for our integral. Is this still integration by parts? Yes, we still follow the formula by integration, or of integration by parts, correct? But this time we had a recurring integrand that needed to be simplified. Okay, so as long as the right side is okay, so we're just following the right side, correct, then the answer is correct. So this is your answer. Now, there are a lot more problems in integration by parts, mixing okay, functions or different types of functions together. And I would suggest you try to solve them on your own. Okay. So what about you try this one? This is now an exponential function and then a trigonometric function. So this can be now evaluated using integration by parts. So this is the first of many techniques of integration. Okay, so before we end this particular lecture or unit, so just recall that integration by parts is applicable for integrands with two or more types of functions involved. Okay, integration by parts is also applicable for integrands with one type of function but could be rewritten into a product of a function u and a derivative dv. Okay, so the choosing of u and dv is very important for integration by parts. Okay. And that's it for integration by parts. I'll see you on the next techniques of integration. If you have any questions, as always, so leave them on the chat box for our Canvas or our email. Thank you.